Hi, everybody. This is Sasha. It is the 9th of May, 2020. And what I'm recording for you right now is a review of I'm going to be going over this final review here. I guess the words eluded me for a moment there. I'm re-recording this because something happened during the Thursday recitation that doesn't need to be on video. And I'm just going to this is a replacement, I'm sure you were told about this, but it's really not worth getting into too much detail about. So I've got the review up here, and I thought that I know some problems you did last week as a review during class, but what I'm going to do is I'm going to basically just do every problem, and we'll see how long it takes me. And I'm going to timestamp the video with the links to different problems. So there should be something, if you look down in the description, about where to jump to for each individual problem. All right, well, let's get started. So that's my email. I can do away with that. So I think I'll make another thing here, and I'll say, oh, I need to say final review, May the 9th. And I'll just make an ordered list here. So the first batch of these problems is about computing limits. And if I remember right, none of these are particularly spicy. Most of these can be done by straightforward evaluation. A couple of them, you're going to need to mess with it algebraically a little bit. And for a couple of them, it looks like you might want to use L'Hopital's rule. So let's get going. So this is A, and that's going to be the limit x going to 1 or 2. This would be a lot easier if I had this up on my phone and I didn't have to tab. Let's actually do that. Well, I'll work on that in between problems so you're not doing something weird. Okay. So first guy is going to be the limit x approaching 2 of quantity 1 minus x squared. And now remember, when I try to work a limit problem, the first thing I'm always going to try to do is just see if I can plug that value of x in. If this function is continuous at whatever value of x this is, in this case 2, then that's going to work. But those are kind of the easy limits because there's nothing more than simple substitution involved. There can also be more complicated, more difficult limits. So, but this one is easy. We just say this is equal to 1 minus 2 squared, which is 1 squared, or negative 1 squared actually, or 1. And that's all there is to that one. And remember, the reason that this sort of works so straightforwardly is that we're dealing with the limit of a continuous function. And what it means for a function to be continuous is kind of that the limits are easy to evaluate. Okay, so let's do this. Next one up, I think, is going to be limit as x goes to positive 4 of the square root of x plus 2. Like the other one, this isn't too terribly complicated. I'm just going to plug in. And you get square root of 6. And that's that one taken care of. Here's another one. I'm going to use display style for this one because there's a fraction in it. This is the limit x going to minus 2 of x squared minus 4 over x to the 8th plus 8. And so, as it happens, this is a pretty straightforward limit because I can plug in immediately and I'll get, allow me to save you some work. This is just going to be 4 minus 4 over 2 to the minus 2 to the 8th is 256. If I add 8 to that, I will get 264, but I don't care really because the top is 0. So that works. A quick detour I'd like to point out is that I don't think there are any problems on the review sheet that require this, but one way that I could change this is to maybe write limit x going to minus 2, I'll say variant, and display style limit x going to 2, minus 2. What if I had x squared minus 4 over another function whose value at minus 2 was 0. So maybe I could pick x cubed minus 8. So I wanted to pick this problem. I wanted to vary this problem in this way because it's an example of what I would call a harder limit. So if I try to plug in immediately, I will get a 0 over 0. And that doesn't really work for me because 0 over 0 is an indeterminate form. That could be anything at all. That could be any finite value, infinity or negative infinity. So I have to be a little bit cleverer about how I go about solving this. So there's two ways that you can do. You can attack this with a spoon or with a bulldozer. Probably the less heavy-handed way to do this would be to factor the denominator and the numerator. And then you'll see that both of these are going to cancel. Since these are polynomials, it makes sense that they would cancel because they're both 0 when I plug in minus 2, right? That means when I factor both of them, I should get an x plus 2 in each of them. The top one gives me difference of squares, x plus 2 times x minus 2. The bottom I've chosen because it's actually a difference of cubes. So hold on a second, this ain't gonna work. I need to make this x cubed plus 8, don't I? That's what I get for making these problems up off the top of my head. So now this really does go to 0 over 0. And I'm going to be able to factor out an x plus 2 from the denominator. This is just because there's a means of factoring a sum of cubes or a difference of cubes. And as it happens, without belaboring it too much, that's going to come out to x plus 2 times x squared minus 2x plus 4. And so we can say that this limit is equal to that one. And now if I Uh-oh. And now if I do my cancellation, I'm going to get x minus 2 on top, and x squared minus 2x plus 4. And now I have to see what happens when I plug this in, because now I believe I can plug in, right? Certainly the top isn't going to go to 0 any longer. That's going to be minus 4. And then if I concern myself with the bottom, that should be 4 minus negative 4 plus 4, yes? And so that comes out to negative 4 over 12, which is minus 1/3. Let me give myself a line break in there because that just looks bad. Okay, there's that. So, okay, like I said, that's the maybe more complicated but easier, or more complicated but more elegant, I would say, way of doing this. If you want to take a hammer to it instead, you can use L'Hopital's rule. Display style. There's a joke about being pretty and stylish somewhere in there, but I'm not going to make it. I'll let you do that. So remember what this says. So if I have a 0 over 0 limit or an infinity over infinity limit, I can take the derivative of the top, which in this case will give me minus 2x, and the derivative of the bottom, which will give me 3x squared, I think, right? And so that actually simplifies now and becomes the limit of 2 over 3x. And now if I plug in, I get my negative 1/3 again. Oh, I've been writing code too long. All these equals equals. All right. So there's that one. Our friend L'Hopital's rule is going to appear a couple more times here. Those are the other two problems I've got. So let's see, D. This is limit x going to 0 of 1 minus cosine x over sine x, right? Now, let's see here. Okay, so there's maybe 3 ways you can do this. Yeah, looks like it. So I'll give you 3 ways to do this one. One is to recognize that this is a quotient of what I would call the magic limits. 2 of them anyway. There's a few more that fall into that category for me, but these are the first ones you learn. Here's what I'm going to do. This is a little trick. I'm going to write this, I'm going to divide the numerator by x, and I'm going to divide the denominator by x. And then you can say, what? You can say, well, I know that the limit of a quotient is the quotient of the limits. So I might put this additional step in there just in case it's, oh, hello, let me copy, please. Hello, yes, please, okay. And so I can say this is the limit x going to 0 of the top over the limit x going to 0 of the bottom. And I'll delete this one out front now because I've taken care of it. And so if you remember your magic limits, you know that that is going to be 0, which is the limit of 1 over cosine x minus x, over 1, which is limit of sine x over x. And so that's a 0. Here's another way to do this one, is just to take our good friend the hammer to it and use L'Hopital's rule. So I'm taking the derivative of 1 minus cosine of x. If I take the derivative of 1, that's going to give me a 0. If I take the derivative of a negative cosine, that's going to be negative sine, so a positive sine. Derivative of sine, of course, is cosine. So you could say at this point I've got the limit as x goes to 0 of tangent, and tangent of 0 is certainly 0. Or I could just plug in and say I've got 0 over 1, and that's 0. So that's probably the fastest way to do this if you know L'Hopital's rule, which you're supposed to, so this is the fastest way to do this then. There's one more trick I want to show you because it kind of exemplifies one of the things you need to be able to do with working with limits sometimes. And that is to multiply by a conjugate. So conjugate is a $5 word for take a binomial and change the sign. The point being that you sort of want to affect a difference of squares. So in this case, here's what I'm going to do. I'm going to take the 1 minus cosine x over sine x, and I'm going to multiply both the top side and the bottom side by 1 plus cosine of x. And now what has this done? This has given me a difference of squares on top, because here's what's going to happen. If I multiply this out, my limit is still out there. We'll take care of it in a second. Over sine x times 1 minus cosine x, or 1 plus cosine x, sorry. Okay. And now from trig, I know that what's sitting in the numerator here is just sine x, sine squared x, right? I got a step ahead of myself because the next thing I'm going to do is cancel. I can fit another 1 in there. Uh-oh, that's not what I want. Insert mode, paste. What I would really like is to be able to do this from inside of org mode, but that's not going to happen anytime soon. So I've got sine squared x sitting here, and now a sine of x is going to cancel, and I believe the denominator then is going to go to something besides 0. To wit, I got to display my style here. I kind of hope I'm going to be teaching next semester again, and I kind of hope it's still remote. Because 1, I won't have to move out of this house I live in. And 2, I can say I have to display my style. Because if I'm writing on a board, I can't type this in math language. So, okay. And if I plug this in, I get 0 on top and 1 plus 1 on the bottom. And so that is a third way of getting 0. Okay, so was doing this 3 ways completely unnecessary? In terms of getting the right answer, it certainly was, but there's more than one way to get the right answer, and I think that's beautiful. And this demonstrates some tricks that are handy to have in your back pocket for limits. Now there's one more, and I believe this one is so powerful that I have to hit it with the hammer. Sometimes the hammer's all you, well, okay. I could get tricky with this one, but then it's beyond the scope of. Okay, this is the limit, x going to positive 1 of e to the x minus 1 sine of pi x over 2. Oh, this one is just you plug in, isn't it? Okay. Well, what I probably should do is to say, this one looks like it's just kind of a plug-in situation, but let me make it a little bit more complicated after I do this one. So I've got e to the 1 minus 1 sine of pi x over 2, or sorry, sine of pi over 2. And now let's see, that's going to be e to the 0, which is 1. And then sine of pi over 2 is also 1. So I believe this is just 1, right? Okay, let's go hard mode now. Because I want to demonstrate a limit for which you must use L'Hopital's rule, or something even worse, but I'll keep it x going to 1. Let me now say 1 minus, let me now say 1 minus e to the x minus 1 over perhaps sine of pi x. Let me display my style. Okay. So I believe what I've done here is to manufacture a limit that definitely does require L'Hopital's rule, I believe, because now I've got 0 over 0. I wonder how many more times I'm going to type hospital's rule. They certainly do. Let's see. So that's going to be display style, the limit, x going to 1. The 1 differentiates away. The negative sign is going to stay out there. And it looks like I'll get pi cosine of pi x. Which looks, let's see, that looks believable to me. So now I can plug this in and I get a 1 on top, negative 1 on top actually. And cosine of pi is negative 1 times pi, of course. So I think my final answer is going to be 1 over pi. That's nice. That's a nice problem. So hammers are good tools. But it helps to know about the other ones just in case the hammer doesn't work for some reason. Sometimes a pair of pliers will do better. Okay, let's see. That should do for limits. Let's do This video is never going to upload to YouTube if I do it in one part. It's going to have to be a series. Shit. Okay. So let's do this. 2, find the tangent line to the graph of f of x at the point c comma f of c, and I need that needs to be in parentheses. So first up, what I should probably do is derive the formula for that and have it here just so it's handy, so I don't have to do the derivation every time. I can just plug in. That's one of the nice things about being a mathematician, is you know when to go general and when to be specific. So, okay. So remember, the tangent line at this point has slope. Well, that's the slope of the tangent line. And when you hear slope of the tangent line after a semester of this class, you'd better be thinking derivative. Specifically the derivative at c. And by assumption, it goes through a point that we know. So we know its slope and we know a point, so we can use point slope form on it. Y minus, I've always heard y minus y naught, but y minus your y coordinate. I think some people use y1. I don't know why. But equals m, that's the slope, times x minus x naught. And so if I plug my values in here, the y coordinate of the point I have is going to be f of c. My slope is, of course, f prime of c. And then I have my x coordinate is c, so x minus c is in there. Or, and I'm going to put this in a box because it's important, y equals, I'm going to write this in mx plus b form, but one thing I want to note here is that if I were to switch around these two terms, then I would have the first two terms in order of what's known as the Taylor expansion of f of x about c, which is a very useful tool that you'll learn about in Calc II. It's about the one thing you learn in Calc II, that and integration by parts, that I would say get used the most, especially in your engineering type applications, and certainly for physicists. So Taylor expansions are very powerful, and they're a generalization of the idea of taking a tangent. So you can take a tangent line, but it's a parabola or a cubic or that sort of thing. That's basically what a Taylor series is. So, or excuse me, a Taylor polynomial. They're almost the same thing. Okay, so I'm just going to use this formula, and now I think I can just plug all these in, right? So now I'm just taking derivatives, and that's okay. So let's see. First one I've got here is f of x equals x squared at c equals 2. So first thing I do is I compute f prime of c. I could also compute f of c first, but I'll do that second. So let me actually take f prime of x first, just so we know that's going to be 2x. That's from the power rule, of course. So f prime of c equals 2c, which is 4. f of c is also 4. That's just 2 squared. So my tangent line, putting it all together, is going to be 4. That's my slope 4 times x minus c. C is 2, plus f of c, which is 4. This is a perfectly valid final answer. You can leave your tangent line in this form and you'll be okay. If not, once I start going back to the gym, I'll find whoever is taking points off for that and suplex them because it's ridiculous. This gives you more information about the function than just writing it in mx plus b form straight up. So, all right. Let's see. That wraps up that problem. Of course, you could simplify it. There's nothing wrong with that, but why when you could just do it like that and save yourself some time? Next one up, f of x equals sine of x. It's c equals pi over 2. So, okay, let me take f prime of c. Derivative of sine is, of course, cosine. So I'm going to say cosine of c there. So, which is cosine of pi over 2, and cosine of pi over 2 is a 0. So what does this mean? It means my tangent line is horizontal. I can also have vertical tangent lines, in which case this formula kind of breaks down because the derivative won't be defined. But those are comparatively rare. And they work very similar to how this problem works. So let me just go ahead and take f of c here. That's sine of pi over 2, which is, of course, 1. And so now I can say my TL, my tangent line, is y equals 0 times x minus pi over 2 plus 1. And this is one instance in which I would prefer to simplify it and say it's just 1, right? Y equals 1. And in fact, let me make it a little bit easier on myself. Let me say y equals 1. Okay. Moving right along. F of x equals sine x. Same function, so it's going to have the same derivative, but c is equal to pi. So f prime of c equals cosine of c, which is cosine of pi, which is, let me see, -1. So there's my slope. F of c is going to be sine of pi, which is 0. That's my intercept, kind of, that's my, so this turns out to be an x-intercept is really what I would say here. TL is y equals -1 times x minus pi plus 0. And if you really wanted to simplify it, you could say y equals pi minus x, or y equals -x plus pi, whatever. So there you go. Equals next up, we've got x cubed plus x minus 3. And c is 1. So here's my derivative. This is a polynomial, so I can get by just on power rule here. F prime of c, that's going to be 3c squared plus 1, and then the minus 3 is going to get differentiated away. So last time I checked, that was 4. F of c, if I just do the math in my head real quick, that's going to be -1. And so my tangent line is y equals 4 times x minus 1 minus a negative 1. I might go a step further without 1 and say 4 times x minus 1 plus 1. Okay, moving right along. Looks like we got a quotient rule coming up here. So I've got f of x equals, got to display my style now because I got a fraction. X plus 2, x plus 1, c is 1. Okay, so there's a couple of ways you can do this. So when you have a fraction and it looks like this one in the sense that the top and the bottom look similar, then you can just, you have the choice to simplify it, so divide it out, or you can just use quotient rule. I'm going to do both of those. I'll do quotient rule first, I think. All right. F prime of c equals, okay, got to display my style. I wonder if I can get that on a shirt. It just says backslash display style on it. Maybe I'll do that once I can. Okay, so let's remember how quotient rule goes. I think it's easier to start with the bottom because that's always the denominator of the original function that's squared. And so now it's going to go derivative of top times the bottom. Top always comes first. So that's going to be derivative of x minus 2 times x plus 1 minus derivative, so now the other way around, x plus 2 times the derivative of the bottom. So that last time I checked was also 1. And that's going to come out to be minus 1, so x plus 1 squared. I'm not going to do it, but you could also have written, I'll tab in here, could also have written, display my style, x plus 2, x plus 1. That's just what I'm going to say next time I'm dysphoric. I got to display my style. And then everybody else will go blind. So let me write it like this. X plus 1 over x plus 1. And then I claim if I split that fraction up and divide it out, I'm going to get 1 plus 1 over x plus 1. And now if I were to take the derivative of this, the 1 would differentiate out, and this is x plus 1 to the minus 1. And if you use power rule on it, you'll get this pretty quick. Oh, and let me just change this to an f of x real quick because I got carried away. So let me say, so f prime of 1 is going to be, let's see here, negative 1/4. And f of 1 is going to be 3/2, I think, right? Okay, yeah. So tangent line is y equals, slope comes first. I'm going to write it like this. And then I've got x minus my x coordinate, that's 1, plus my y coordinate, that's 3/2. And I could just leave it like that or combine fractions if you want, but I don't see the point in doing that. Let's see. think I've got two more, and these get a little bit tricky. So this is f of x e to the square root x c equals 4. And so let me take a derivative first. This looks like a chain rule situation. So the first thing I should do is I start from the outside with chain rule and I work my way in. So the first thing I'm going to do is differentiate the e to the something part. And so that doesn't change that part. That's just going to be the same e to the square root of x. Now the chain rule kicks in because I have to multiply by the derivative of the something. In this case, the something was square root of x. So that's going to be square root of x is x to the 1/2. So I take the derivative, and that should be 1 over 2x to the minus 1/2 times x to the minus 1/2, or a little bit formatted a little bit more nicely. That's going to be 1 over 2 square root of x. Oh, I forgot my space. There we go. And so now, okay, f of x equals, or sorry, f prime of 4 equals e to the square root of 4 times 1/4. So e squared over 4. And then f of 4 is just my e squared. So my tangent line finally turns out to be y equals e squared over 4. Let me just write it like that. And then I've got x minus 4 plus e squared. And this actually does simplify a bit, so I'm going to go ahead and do that. If I multiply this whole thing out, I'm going to get e squared over 4 times x minus e squared plus e squared, which is just e squared over 4x. Okay. One more, and then I think I'm going to stop the recording here so that I can upload these and have a video that's less than my entire hard drive. So 5e and c equals minus 3. Okay. So this one might actually be the easiest one. I would note that this function is a constant. That means its derivative is automatically 0 because the derivative is the rate of change and it doesn't change. And so I compute, if I were being very, so f of c is automatically 0. F prime of c is automatically 0. It doesn't matter what c is. And so f of c is going to be, let's see here, just 5e, right? That doesn't depend on the value of c either. So my tangent line is going to be y equals 0, x minus negative 3, plus 5e, and if I get rid of the 0 part, that's just y equals 5e. So if I have a line and a constant counts because it's a horizontal line, the message here is that the line is its own tangent line. And if you think about that for a second, hopefully it will make sense. All right, I'm going to kill the recording now, and I will immediately start again with some implicit.